Welcome to Applied Business Analytics. This is a short video on Lasso Regression. As we talked about when we did ridge regression, imagine linear regression again, where you have a y and you have an x. You want to relate x to y. So essentially you want to fit a line to this data set. And we can arbitrarily fit a line, and there are many lines you can fit to a data set. And how do you fit a line to a data, and how do you know whether it's a good fit? Well, we talk about our line being y hat, and the equation line is y hat equals b0 plus b1x. And of course, we're just doing 1x to make it easy to see here, so we can visualize what's going on. In practice, of course, you would have many, many x's that you put in your model. Well, y hat's what we call our predicted value, and then y, of course, is our observed value. And so for every xi, there's going to be two y's. There's going to be the predicted y and the observed y. Ideally, we'd like them to be the same, but in general, there's going to be noise in the model. They're not going to be the same. We define EI to be our error, also called the residual, and it's observed minus predicted or fitted value. So we might call that our fitted value, or in the context of data science, we often call it our predicted value, and that's what EI is. Observed minus predicted value. You want all the EIs to be zero. They'd be fantastic. That generally is not going to happen unless it's exact relationship. Sometimes the EIs are bigger than zero over here. Sometimes this EI is less than zero. This EI is around zero, approximately. But the EIs are useful to figure out how to fit a line to your data set. The EIs are used for a criterion function. So we might say, what's our objective function? If I could spell objective correct. What's our objective function, also called our criterion function, or criteria, or criterion function? So how to fit a good line. What does it mean to fit a line to data? To fit a line means you want to find B0 and B1. The equation of the line, of course, is B0 plus B1x. So if I know what B0 and B1 are, I can draw the line. So fitting line to data is an optimization problem. It means finding good values of B0 and B1. The method of least squares says find the values of B0 and B1 that minimizes this objective function. You can also write this simply as the summation of EI squared. And that's very popular. It's a continuous objective function. You can take derivatives. You can find the values that minimize it very easily. There's a method of least absolute deviation. There's another way to fit a line of data where you find B0 and B1 that minimize the sum of the absolute values. It's a different line. Sometimes they're the same, but in general it's a different line. This line is less susceptible to outliers than the previous one, but there are different ways to fit lines to data. And why stop there? There are many other ways you can fit a line to data. Lasso regression says find the line. Find B0 and B1 that minimizes the following. Lambda is something we bring to the table. It's a penalty term. We bring it to say for a given lambda, minimize this. And we can write this as the summation of EI squared plus lambda times the absolute value of B1. And if you had more x's in the model, it'd be lambda times the absolute value of B1 plus the absolute value of B2 plus so on and so forth. It's just the simplest version of this. Lambda can be any value from 0 to infinity. If lambda is 0, you're back to least squares. And as lambda gets bigger and bigger, B1 is going to get smaller and smaller because you're trying to minimize this expression. You're trying to make this as small as possible. So if lambda is really big, B1 is going to get shrunken closer and closer to 0. Never go exactly to 0, but it'll get shrunken to 0. Actually, one nice thing about Lasso as opposed to ridge regression is it can actually go exactly to 0. And ridge asymptotically gets closer and closer to 0. In Lasso, it can go exactly to 0. And this just gives you a different line. Instead of doing least squares, you're doing a different optimization. You're finding B0 and B1. You're finding the same components of a line, B0 and B1. It just gives you a slightly different line. Now, why do you need a different line? Least squares regression is great if you have one data set and want to explain how the x variable relates to the y variable, but it may not generalize that well. It also has issues when the x variables are highly correlated with one another, what we call multiclinarity, or when the number of x variables is high relative to the rows of data. Now, ridge produces a line that may generalize better other unseen data, so does Lasso. So ridge and Lasso, we should say here, produce different lines. They have different penalty factors. So ridge is minimize EI squared plus lambda B1 squared. Lasso is minimize EI squared plus lambda absolute value B1. And in the next video, we'll actually compare the two and show you get different fits. But the idea is for giving up some optimality on the data set right in front of you. Least squares is the best thing. You have one data set in front of you, least squares is the best thing to do. Does it generalize to other data you haven't seen yet? Not that great. However, if you are suboptimal to data you see in front of you, you might get better predictions on other data you haven't seen yet. And that's the philosophy behind Ridge and Lasso. So summary, Lasso regression works by attempting to increase the bias to improve variance. You're not optimal on the data right in front of you. That's least squares. However, you might get better predictions on data you haven't seen yet. The model performance might be a little poor in a training set, the data right in front of you, but will perform consistently well on both the training and testing data sets. Whereas least squares performs really well on the training data set, but may perform horribly on the test data set. Lasso has an advantage over Ridge. In Lasso, the coefficients go to zero as the penalty value lambda gets larger and larger. In Ridge, they asymptotically, but they don't get zeroed out. In Lasso, they actually get zeroed out when lambda gets really big. So that's one advantage Lasso has over Ridge. As a quick example of this, the blue line is least squares, and these are different values of lambda. So it's like lambda equals 0. This is lambda equals 0.5. This is like a lambda equals 1. This is a lambda equals 10. And you can see as lambda increases, the slope gets smaller and smaller. In fact, here, the lambda, for a large lambda, the B1 is essentially 0. There's no relation between y and x. So unlike Ridge, Lasso can set some coefficient values to 0, making it useful for feature selection. So for large enough lambda, it'll zero out some b's that say you don't need those x's in the model, and what you concentrate on only what should be the important x's that drive the value of y. So now ideally, you've seen Ridge and you've seen Lasso. Next video we have is showing you how to implement all this in R and how to get output.